Hi there, Mr. Sutton here with the IM3 8.3 Part 2 homework solutions on mostly experimental probability for this one. For this one, we had a survey of 2,392 adults, and we want to know what kind of food they're likely to choose at a restaurant. The results are down in this figure here, this pie chart. So we want the probability an adult chosen prefers Italian food. Okay. Well, our probability is, this is more of an experimental probability. We can't really do a theoretical one, but it's basically going to be something divided by our total of 2,392 adults. So something over that is going to give us the probability that a person randomly picked likes Italian. So we just need to figure out how many people actually said Italian in this pie chart. Italian is this color right here, this kind of pinkish color. So that's 526, and rather than try reducing this, we're allowed to express this as a percentage, which I'm going to do now on the calculator. So 526 divided by 2392 gives us, and so this is the decimal version of a percent. You have to move the decimal over twice to get the actual percent, and we'll round this off to the nearest tenth of a percent. So that's going to be, let's see here, 22.0%. For this one, we have a six-sided die that's rolled 60 times, and we've got the results down here in this table. We want to know for which number on the die is our experimental probability of rolling the number, the same as the theoretical probability. So let's get our theoretical probability first. That's probably the easier out of the two. So we have a total number of possibilities when we roll this die of 6 different numbers. So our probability of any number is going to be something over 6. And each number is represented only once on this die, so we have a probability of 1 over 6 for any particular number. So now we're going to go through the experimental results and see which of these match up with this probability of 1 over 6. Let's start with the probability of 1. So our total number of possibilities is really, when you're doing experimental probability, that's the total number of trials, which was 60 in this case. The die was rolled 60 times. So probability of 1 is going to be something over 60. In this case, the 11 over 60, which does not reduce to 1 over 6. It's pretty close, but not quite. So now we do 2 here. That's going to be 14 over 60, which reduces to, let's see, we can reduce by 2's. That's 7 over 30, not 1 over 6. And then probability of 3, that's 7 over 60, which does not reduce to 1 over 6. Probability of 4, that's 10 over 60. That does reduce to 1 over 6. So that's a good answer. But let's double check. They never said that there was only one possible answer. There might be another. So probability of 5, that's 6 over 60, which is 1/10, not what we're looking for. And then probability of 6 was 12 over 60. That reduces to 1/5. Pretty close, but still not what we want. So then 4 was the only number whose theoretical and experimental probability was the same, so our answer is 4. For this one, we have a map showing the length in miles of shoreline along our Gulf of Mexico, and we want the probability that a ship coming ashore at a random point, maybe there was a storm and it was just washed ashore somewhere, we want the probability it lands in each of these given states. So this is one where, supposedly you have an equal chance of hitting any particular mile along this coast. So for our theoretical probability here, we need to find the total possible outcomes, and that's just, the total miles that you could hit here. So for that total, we've got the shoreline of Texas here, 367 miles, plus Louisiana, 397, plus Mississippi, which is only 44 miles, and Alabama's pretty close to that, 53, plus Florida, which is the big winner with 770 miles of Gulf of Mexico coastline. Okay, so what's all that add up to? Calculator time. So adding all that up, we come up with 1,631 miles of gorgeous Gulf of Mexico coastline. And now to figure out the chances that you wash ashore on Texas, well, that's going to be the Texas coastline, 367, divided by the total possible here of 1631. And let's just convert each of these to a percentage. So I'll do that on the calculator. So 367 divided by 1631, that's going to be 22.5%. Now for Alabama, we're going to have 53 over 1631. And back on the calculator, let me just yank my input from before, and I'll replace the 367 with just 53. Enter, and that's only like a 3.2% chance for Alabama. Okay, how about Florida? This should be a big chance here. 770 over 1631. Not going to be quite 50%, I don't think, but let's go back and see what it is. Let me go back 2 inputs just so I have something with 3 digits there. So 770 over 1631, that's 47.2%. And then Louisiana, 397 over 1631. And going back here, I'll just go back here because 367 and 397 are just 1 digit different. Change out that 6 with a 9, press enter, and this is 24.3%. For this problem, we have a bag with 5 marbles of each of a different color, and we've drawn one and put it back in there, and we did this 30 times. The table shows what we got each time. We want to know which marble has the same experimental and theoretical probability. So theoretical probability, that is just if you draw one of these marbles, the chances that you get any particular color. So we have a total number of possibilities of 5. There's 5 different marbles, each of a different color. So our theoretical probability is going to be something over 5. And if you're just doing this for a single marble, then you have a 1 out of 5 chance of getting any of these particular marbles. Now for the experimental piece of this, we're just dividing how many marbles we actually got by the number of trials, which was 30. So let's just go in order. Let's do white first, probability of white. So that's going to be something over 30 because there were 30 trials. Now, how many actually came back white? That was 5. And we can reduce that to 1 over 6, which does not match the theoretical probability. So we're going to keep doing this, and I'm actually going to do it for the other 4 marbles just to show you what they all come out to. So let's do the black one next. That's again going to be something over 30. In this case, 6 over 30, which reduces to 1 over 5. So that's most likely going to be our final answer. It matches our theoretical probability. But moving on to red, so that again has a denominator of 30. This time we have 8 for the numerator, and that reduces by 2s to 4 over 15. Not what we want. Green, so total number of possibilities is 30 still. Now we have 2 actual outcomes that we wanted. So that's 1 over 15. And then finally blue, 30 is the denominator. 9 is the numerator now, and that's 3 out of 10 if we reduce that, or 1 out of 10 rather. So that's going to be then the black marble that gave us the same experimental and theoretical probability. Final answer, black marble. For this problem, we have a spinner with 4 equal area sections, and it's spun 20 times. Table below here shows the results from doing that for each color. We want to know for which color is our experimental probability of stopping on a color, the same as the theoretical probability. Well, since all these 4 areas are equal, the theoretical probability for any particular color is going to be the same thing. So we have the total possibilities, of which there are 4, and then the theoretical probability of just one of those colors is going to be 1 over 4. So we're looking for something whose experimental probability is also 1 over 4. Well, experimental probability is basically desired outcomes over total trials. So if we want the experimental probability, for example, of red, well, how many total trials do we have here? Well, they told us it was 20 times, but you could add these numbers together and get 20. So it's going to be something over 20. Now, how many of these actually came back red? In our table, it says 5 did. So we have 5 over 20 is the experimental probability of red. And then that's just going to reduce to 1 over 4, which is what we were looking for. Now, rather than stop here, I'm actually going to go and calculate the other experimental probabilities as well. Practice makes perfect, and also they never said that it was just going to be a single color. You know, there might be more than one answer here. It's not multiple choice. So doing the greens now, we again have 20 for our denominator because there were 20 trials, but now 9 is the numerator because 9 actually came back green. For blue, we have 20 for the denominator, and desired outcomes there were 3. None of this is reducing to 1 over 4, of course. And then for the yellows, we had a 20 on the bottom and a 3 on the top, just like the blues. So when all is said and done, red is the only one whose theoretical and experimental probability was the same. So red is our answer. For this one, we have the age distribution of an event. We want the probability of each of these events here. So let's see here. We've got a person chosen at random is at least 15 years old. So you basically have to look at this table and figure out probabilities based off of the traits that they're giving us here. Now, a person being at least 15 years old, another way of saying that is that the person is, let's see, if they're at least 15 years old, that's like saying greater than or equal to 15. We're basically saying that they're not less than 15. That's another way of doing that. Because greater than or equal to 15, there's a whole bunch of age groups that falls into. There's way fewer groups that don't meet this criteria. So it's probably faster just to exclude the ones that don't meet this criteria. So to find that, I was just going to start with 100 and subtract the less than 15s. So we have, let's see, under 5, that's a 7. We'll subtract that. We don't want them. And I'm also in the parentheses here to the 7, I'm going to add this other group of less than 15s, the 5 to 14s, the 13% there. And then that's 100 minus 20% of those people who were less than 15, giving us 80% of people who are at least 15. So that's one way of doing it. If you wanted to, you could just do 14 plus 13 plus 13 plus 15 plus 12 plus 13, but that seems like more work. Now, our other part of this, a person chosen at random is 25 to 44 years old. Well, we have to add 25 to 34, which is 13%, to this other category of 35 to 44, which is another 13%. So that's a grand total of 26% that fall in that age group that give us a probability of picking one of those people.